We're going to begin our next unit by studying radicals and radical equations. Now, the radical symbol you're actually familiar with. In fact, when I draw it, most times students say, well, Miss Nona, that's the square root symbol. And indeed, a radical symbol can be a square root symbol, but what you're going to learn is that there's actually other roots. There's what we call a cube root, maybe a fourth root. And the reality is we can find any root. So all of these are radical symbols, but only one of them is a square root. Now, you're familiar with the square root. If I asked you to find the square root of 16, you'd be looking for two numbers that multiply to be 16. So we know that that's 4. But what if I asked you to find the fourth root of 16? Well, now you'd be looking for 4 numbers that multiply to be 16. And of course, they have to be the same 4 numbers. Now, that would be the number 2. And maybe if I asked you for the third root of a number, well, now we'd be looking for 3 numbers that multiply. In this case, 3 numbers that multiply to be 8. Did you think of them? It would actually also be 2. So you can see when we talk about radicals, we sometimes can get the same answer, but it doesn't represent the same thing. But all of these, they definitely are roots, and roots are the same as radicals, and they always will break a number down as we've done with each of these. Now, what we want to do is now take a look at what it would look like if these numbers are graphed. What would be the graph of a radical equation? And that's our first order of business, is to realize that if we have something like y equals the square root of x, that indeed is a radical equation. It's also an equation that we haven't actually graphed yet. We've graphed a lot of equations this year, but we haven't seen what it looks like if we graph something like the square root of x. Now, we can always start with a table of values. It's always a good place to start with any graph. When you have a table of values, you're able to basically plug in x and get the y value. So maybe we'll start with plugging in numbers like 0, 1, or 2. Now, when we plug in 0, what we're really doing is we're taking the square root of 0. And the square root of 0 is still 0, because, of course, 0 times 0 is 0. What about the square root of 1? Same idea. What are 2 numbers that multiply to be 1? Well, they would still be the number 1. How about the square root of 2? Now, it's not something that I expect you to know without a calculator, but you could type it in a calculator. It comes out to be a decimal. The main thing I want you to realize is that the reason that it's 1.41 is because if you multiply 1.41 times itself, you will get 2. You're also going to learn that it can be nice to pick nice numbers, like numbers that have even square roots, like the square root of 4. Okay, the square root of 4 is easily known, and so the output would be 2. How about like 9? How about the square root of 9? Well, of course, the output of that would be 3. And can you think of one more that should go in this table? It would make sense to use 16, as the square root of 16 is 4. Interesting. What if we try to plug in something like the square root of -9? What if we try to use -9? Well, we've learned that the square root of a negative number is imaginary, but we're not able to graph an imaginary number. And so when it comes to input-output, it would be smart to say that has no output, that is undefined. And what this means is that we can't plug in a -9, and as you'll realize quickly, we can't plug in any negative number. Let's take a few moments and graph these values. If you have the graph paper, or if you have the problem printed out, you can graph here. If you don't, you can just make a basic sketch. Realize that the whole point behind this graph is to start to see a pattern that's forming with the shape of these numbers. I've graphed the first 3. I'm going to move out now to 4, 2. 9, 3. and 16.4. Okay, it's not a graph that we've seen before, but there is a shape to this, and of course when you connect the dots, you're able to actually visually start to represent that pattern. What we have here is a graph that has a slight curve to it. It does grow slowly as it continues to go to the right. Okay, and this would be the graph again of y equals the square root of x. Let's analyze this a little bit. Let's analyze it for its domain. Domain, of course, is x values. When you think about x values in this problem, you can look at your table of values, as we already discussed, that those values are all positive or 0. You can also see from the shape of the graph that the domain appears to also continue to go greater than 0. And of course, we can write that as an inequality, or we can write that in interval notation. If you look at the range of the graph, of course, that would be the y values. And same thing, you can look at your table of values. It looks like those y values are also greater than 0, which is also being shown by the graph itself. So our range is y values that are greater than or equal to 0. Now, I've said a couple times that you haven't seen this graph, although that isn't completely true. We've actually seen this graph in our conversations of inverses. Inverse was something we looked at in the last chapter, and if we just go back to that idea quickly, you can actually find the inverse of this original equation. All you have to do is switch x and y and solve for y. Now, when you switch x and y, you get x equals the square root of y. When you try to solve it for y, you end up getting x squared equaling y. And that means that the inverse is x squared. Now, the thing about this inverse is that it has to have symmetry, as all inverses do. It has to have symmetry with this diagonal line y equals x. So when you think about graphing something like y equals x squared, when you think about graphing the inverse, you're actually only able to graph half of your parabola. And when you graph half of your parabola, you end up switching all the points that we plotted before, and we end up with the inverse. Now, since we only graphed half of the parabola then as our inverse, we have to make a little restriction on this answer we got, and that restriction is to say that we're only going to end up with x's that are greater than or equal to 0. In other words, the right half of that parabola. All right, so the radical equation. Let's graph some other variations of this, ones that have some adding and subtracting. In other words, some transformations that have occurred to the original equation. And before we do this, it's usually helpful to think about what type of x values you're going to want to plug into your table. And that actually is just the same thing as the domain. Now, it turns out that the domain always involves the part of the problem that is under the radical, in this case, the x plus 5. And it's always going to be true that whatever's under the radical has to be greater than or equal to 0. Now, the reason that that's the case is because we can't take the square root of a negative number. So if we say that x plus 5 has to be greater than or equal to 0, in effect, what we're doing is we're actually finding the domain. And, of course, when you solve this with some simple algebra and end up actually getting x is greater than or equal to negative 5, then you're able to start to generate your table of values. You see, your table of values would have to start at negative 5. And as it says, to be greater than negative 5 would give us some additional numbers that we could plug in. Maybe like something like negative 4. maybe something like -1. Now, you might ask, well, Mr. Naylor, why did you skip to -1? Let's take a look at that by plugging in some of these numbers into our equation. Now, when you plug in -5, you're going to be taking the square root of -5 plus 5. Well, of course, that's going to be the square root of 0. But after you do the square root of 0, you're going to have to subtract 3. So we end up getting a final answer of -3. What happens if we plug in -4? Okay, well, when you plug in -4, you're actually going to be taking the square root, this time, of 1. And the square root of 1, of course, is still 1. And when you subtract 3 from that, you end up with -2. So why did I skip down to -1? Well, the idea here is that you want to be plugging in numbers that give you nice square roots. In other words, even square roots. And if I plug in -1, I find out that I'm actually going to take the square root of 4. 4 is a nice even square root. And of course, when you take the square root of 4 and you get the number 2, you still have to subtract 3 from that, which will give us a final answer of -1. So what would be another number that would be a nice number to plug in? What would be another number that would be nice to plug in here and add 5? Well, you want to be thinking about getting, again, a nice or an even square root. Okay, how about getting the square root of 9? Now, that doesn't mean I plug in 9. It means that I plug in 4. So I'm going to get the square root of 9, which comes out to be 3. And of course, after we subtract 3, we'll end up getting 0. So I plugged in 4 so that I could get 9, which turned out to give me 3 minus 3. We have space here for one more number to plug in. But what we really want to be asking ourselves is, what's the next nice square root after 9? Okay, if you're thinking 16, you're on the right track. Okay, but that doesn't mean I plug in 16. It means that I actually plug in 11. Okay, because again, when you plug in 11, you get the square root of 16. Square root of 16 is 4. And when you subtract 3 from that, you end up with 1. It took a little while to get this table of values, but you get the hang of it. And remember that it all started with finding the domain. And the domain is always what makes, is always connected with the part that's under the square root. And again, we want that to be greater than 0. Let's graph this table of values. What I really want you to see when you graph it is the same shape, the same radical graph. Okay, because a radical graph is always going to have this shape that grows and slowly curves as it makes its way to greater and greater x values. Now, the one thing about this radical graph is that it did have a different starting point, and you're going to begin to realize that that starting point is really the most important point. In fact, we'll call it the vertex. I just want you to notice it. One of the reasons that it's really important is because it's really where the domain and the range always start. In this case, our domain, which definitely goes greater than -5, but notice that it started at -5. And our range that definitely goes greater, this time greater than the y value, which is -3, to infinity. What about this next equation? It's a little different. It's got, first of all, it's got a negative sign in front of it. Now, that's fine. You're allowed to have a negative in front of a square root. Also notice that we've got two numbers under the square root, which is really where we want to start when we think about the domain. Now, what I'm doing here is I'm finding the domain algebraically, meaning that I'm thinking about the 2x minus 8 and the fact that whatever's under the square root always has to be greater than or equal to 0. The reason that this is the case is because you can't take the square root of a negative number. So we always need to have positive numbers under the square root. Now, if you solve this equation, pretty easy algebra, you just add 8 and you divide by 2. And of course, if you add 8 and divide by 2, you end up with x being greater than or equal to 4. So again, that's going to be our domain. I actually could write that domain right now if I wanted to, but notice that that also is where my table of values is going to start. It's going to start at 4 and choose numbers that are greater. Now, sometimes it can be challenging to decide what kind of numbers to plug in to a radical equation, and that's why you'll see that I've given you some of the numbers here, but I still want you to see what happens when you plug in. You should catch on quickly, however, that whenever you plug in your first number, well, the reason it is the first number is because that's going to end up giving you 0. So we take the square root of 0, which still comes out to be 0 when we plug in 4. Now, if you plug in 6, you end up with the square root of 12 minus 8. And I want you to see that 12 minus 8, it gives us, so to speak, a nice square root, an even or perfect square number. So, of course, that comes out to be 2. But we have that negative sign in front, and so we want to make sure that when we get 2 that we actually make it negative. What would happen if you plug in 8? Okay, well, I'm allowed to plug in 8, but what you'll see is that, oops, got a little bit of a mix-up here. What you'll see when you plug in 8 is that it doesn't come out evenly. And we want to make sure we understand that that's okay. You're allowed to plug in numbers like that. It just might require a calculator as you try to compute, of course, 16 minus 8 as you try to compute the square root of 8. Now, the square root of 8 does exist. It actually is equal to 2.83 using your calculator. And, of course, with the negative sign, we end up with negative 2.83. So I certainly can get that number. It's just a decimal, and maybe it'll be a little tricky to graph. What if we want to end up with one more, again, perfect square root? We had the square root of 4 a couple moments ago. What if I want to get, again, a square root that is perfect? Can you think of a number that we could plug in? What about if I want to get like the square root of 16? What if I want to get the square root of 16? That doesn't mean that I plug in 16. It actually means that I have to plug in 12. Okay, because when you plug in 12, if you do that carefully up here, you're going to end up getting 24 minus 8. And 24 minus 8, well, that does come out to be 16. Okay, now, of course, we want to do the square root of 16, and that we know is the number 4. With the negative sign in front of it, we end up with negative 4. Okay, again, it can be kind of tricky sometimes to decide what numbers to plug in. They might be given to you, but also part of the point behind this problem is to graph it. I think we have enough information to make a graph. We can start graphing our points. I want you to notice after you graph 4, 0, and I move to 6, negative 2, I want you to start to notice the direction of this graph, the direction that the points, that the pattern of the points is starting to make. Now, I did graph the decimal. I'm going to have trouble graphing 12, negative 4 because we're running out of space here. I could still get an idea, though, that graph or that point is going to be somewhere out here, again, at 12, negative 4. But the main thing is to see the shape of this graph or the direction of this graph. It is indeed going down, but it still has that slight curve to it. It still has this most important point, this starting point or vertex, which has everything to do with our domain and range. As you can see, our domain is still going to the right from this point, but I want you to notice that now that the graph's going down, that we would have to say our range is going down from 0. Now you could say y is less than or equal to 0. That means that we're going down from 0. If we were going to use interval notation, we would make sure that we write it as negative infinity comma 0, because you always want to write the smaller number followed by the larger number. We can also use interval notation on our domain if you'd like to do that. Well, do all radical graphs look like the square root graph? The quick answer is it depends. What it really depends on is whether it's an even or odd root. You see, a square root is an even root. And when we think about even roots, you cannot identify the even root of a negative number. But when we look at an odd root, well, it turns out that we can. And so if it's an odd radical, the graph's going to look a little bit different than if it's an even radical. And the easiest way to find this out is by looking at a table of values where we actually can evaluate a negative x value. Now, what I'm talking about here is if we try to do the cube root of negative 8, that would be like trying to find 3 numbers that multiply to be negative 8. Well, yes, there are 3 numbers that multiply to be negative 8. It would be negative 2 times negative 2 times negative 2. If you think about those 3 negative 2's, they indeed would come out to be negative 8. You can also do the cube root of negative 4 is a decimal, but 3 negative 1.59, 3 of those are going to come out to be negative 4. And I could do the cube root of negative 1. Here I'm looking for 3 numbers that multiply to be negative 1. Of course, they always have to be the same 3 numbers, and the answer works to be negative 1. If you try it, negative 1 times negative 1 equals negative 1. So the truth is I can do the cube root of a negative number. I can also do the cube root of 0, and I can also do the cube root of a positive number. If you plug in 0, you get 0. If you plug in 1, you get 1. And just one more time, if we plug in 8, we're looking for 3 numbers that multiply to be 8. Of course, they have to be the same 3 numbers, and those 3 numbers would be 2, 2, and 2. Now, when you graph this table of values, you find out that there's some similarity and there's some differences to the ones that we did above. Take your time and graph. There's negative 8, negative 2. Here's negative 4, negative 1.5. And moving a little closer, we get negative 1, negative 1. We have 0, 0. And do you see what the shape of this graph is starting to look like? It has 2 sides, and both those sides, when connected, will make a cube root graph. And so it's similar to the square root graph, but again, we have 2 sides because we're able to do the negative x values. All right, so I thought what we would do here is look at one more radical equation and just go a little bit deeper than graphing it, where we would think more about analyzing it. Analyzing it involves thinking a little bit more about the behavior of the graph beyond just, again, just a table of values. It is helpful, though, to just one more time realize that your table of values has everything to do with the domain, which has everything to do with the part that's under the square root. And the expression that's under the square root, x minus 5, that always has to end up being greater than 0. So some simple math here, we would say that, of course, x itself has to be greater than or equal to 5. And you can see that that's where my table of values is starting. It's starting at 5, which is the first number that we want to plug in. Now, when you plug in 5, you end up, as always happens, we end up getting the square root of 0. Now here the square root of 0 times 2 is still going to come out to be 0. When you plug in 6, you get the square root of 1. Of course, that's 1, but we want to multiply that by 2. So that, of course, will make it 2. I already plugged in 7. But what I'm doing here is giving you a chance to think what would be another good number to plug in. I mean, could I plug in 8? Sure, I could plug in 8. That's going to end up giving me the square root of 3. I don't really want to do the square root of 3, so why don't we plug in 9? If you plug in 9, you're going to get the square root of 4. Now, I do like doing the square root of 4 because I know that that's equal to 2. And of course, when we multiply it by the 2 out front, we will end up getting 4. Can you think of one more number that would be smart to plug in? Are you thinking about trying to get 9? Now, to get 9, that means to get the square root of 9. I don't want to plug in 9, but I want to plug in 14. So again, I'm trying to get 9. In other words, the square root of 9. I know that that's equal to 3. And after I get 3, I'll multiply it by this 2. And that comes out to be 6. Okay, so we plugged in 14 to get the number 6. Now, why don't you go ahead and graph these 5 points. You can pause the video to make that go a little faster. Then we'll go through analyzing it with these I guess it's actually 6 questions. For some reason, it's labeled up to the number 7, but we'll answer these 6 questions. All right, so we got our radical graph. It actually looks like a lot of the square root graphs that we saw in the front of the paper. So let's analyze a little further. Is this graph a function? Well, remember, a function just has to pass the vertical line test, and so it looks like this does that nicely. How about increasing? Now, what I was looking for here is to say, when is the graph increasing? Now, remember, increasing just means as you move to the right, that the graph's going to be going up. Well, it looks like as you move to the right, that the graph is always going up. So that means that this graph is increasing from its starting point, which is 5, and it continues to increase to infinity. Now, remember, decreasing would mean that the graph would have to be going down. This graph does not go down, and in fact, it's never going to go down. So it's never going to be decreasing. What about f of 30? Now, remember, f of 30 is referring to the when the x value is 30, what y value would you get? So we can plug in 30 very easily into this equation. Of course, when you plug in 30, you're going to end up getting the square root of 25. Which once you compute that to be 5, you'll end up with 10. So again, we got the square root of 25, and once we got that to be 5, our final answer can come out to be 10. Now, if I had enough space on my graph, I'd be able to mark the point 30, 10. Of course, we don't really have enough space to see that point, but it would be somewhere out here, again, at 30, 10. How about question 5? When does f of x equal 6? Now, remember what that means is that the y value is equal to 6. So once again, I can plug that in. But when I plug in 6, what I'm really doing is setting the equation equal to 6 and then solving for x. Of course, when you solve an equation like this, for x, you have to kind of work backwards. You have to work from the outside to the inside. Dividing by 2 would be a great first step. That's going to end up giving you, of course, the number 3. After I divide by 2, I'm going to have to undo the square root sign, which that will require you to square both sides. Now, when I square both sides, that's going to end up giving me the number 9. And I'm kind of running out of space here, but we'll write 9 equaling x minus 5 so that we can add 5 and get our final answer, 14. Now, what has really happened here is that we verified what we already found, and that is that when the y value is 6, the x value is going to be 14, the exact same thing we found from our table. How about question 6? That's an inverse question. Maybe it would be helpful to think about the inverse. Remember, the inverse is always found by reflecting over the diagonal line, y equals x. It can also be found by switching points. I don't know if we have enough time to switch every point, but we certainly could switch 5, 0 to be 0, 5. And when I switch that to be 0, 5, I find a starting point, and then with a little bit of symmetry, I'm able to draw my inverse graph. Now the real question here is this inverse graph, is it a function? And all I got to do is think real simply about some vertical lines, and it passes the vertical line test nicely. So we can say, yes, the inverse is a function.